Hello, we start chapter 4, which is the elementary number theory and methods of proof. In fact, we focus more on the methods of proof. The first section of chapter 4 is direct proof and counterexample. This is an introduction to direct proof. Before we get into this section, we need to know some assumptions. First, in this text, we assume a familiarity with the laws of basic algebra, which are listed in Appendix A of the textbook that you can read, but I don't think that you have any problem with the basics of algebra that we are going to talk, because these are very, very basic, and I'm sure that all of you know about this. Then we also use the three properties of equalities for all objects A, B, and C. A is equal to A, so any object is equal to itself. And if A is equal to B, then B is equal to A too. And in the third property, we have if A is equal to B and B is equal to C, then A is equal to C. That's the transitive properties of equality. In addition, we assume that there is no integer between 0 and 1, and that the set of all integers are closed under addition, subtraction, and multiplication. That means sums, differences, and products of integers are also integers. So these are some basic assumptions. And the last assumption is most quotients of integers are not integers. This is obvious. For example, 3 divided by 2, which is equal to 3 over 2, is not an integer, and 3 divided by 0 is not even a number. First, in chapter 4, we define an even integer and an odd integer. As you know, an integer n is even if and only if n equals twice some integer. So that means there is some integer that n is equal to 2 times that integer. And an integer is odd if and only if n equals twice some integer plus 1. So if symbolically we want to show that, then you will understand better. As you see here, the first row is about the definition of even integer. We say n is even if and only if there exists some integer k such that n is equal to 2k. And n is odd if and only if there is some integer k such that n is equal to 2k plus 1. So let's see an example of the book about even and odd integers. It basically says use the definitions of even and odd integers to justify your answer for the following questions. We have 4 questions. The first one is 0 even? And the answer is yes, because 0 can be written as 2 times k, where k is 0. So that's the reason. You just need to say in the definition we have integer k that should exist. So in this case, k is equal to 0. In part B, we say is negative 301 odd or not? The answer is yes again, because negative 301 can be written as 2 times negative 151 plus 1. So in this case, k, which was in the definition of odd numbers, is equal to negative 151. The third case says if a and b are integers, is 6a squared b even? This is a squared b. That is mistakenly written as a2b, but it's a squared b. So is 6a squared b even or not? And the answer is yes, because 6a squared b is 2 times 3a squared b. So since a and b are integers, then a squared b is integer and 3a squared b is integer, because product of integers will be integer, because integers are closed under product operation. So this 3a squared b is considered to be the integer that we represent by k in the definition of even numbers. So 6a squared b can be written as 2 times k, where k is 3a squared b in this case. So that's the proof for part C. And in the last part, which is part D, we have if a and b are integers, is 10a plus 8b plus 1 is this number is odd or not? So the answer is yes, because we can write 10a plus 8b plus 1 in the form of 2k plus 1. This is 2 times k, which is this number, which is 5a plus 4b. And since a and b are both integers, 5a plus 4b is an integer. So it can be considered as k in the definition of odd and even numbers. So the answer to part D is yes. Next, we define a prime integer. We say an integer n is prime if and only if first n should be greater than 1. That's the first condition. And then the second condition is for all positive integers r and s, if n is equal to rs, then either r or s equals n. And then obviously an integer n is composite, which means is not prime, if and only if first of all n should be again greater than 1, and n should be equal to rs for some integers r and s, such that r and s both are greater than 1 and less than n. So if you want to look at it symbolically, here is the definition of n is prime in a symbolic way. We say for every positive integer r and s, there is a universal statement, as you see. If n is equal rs, then either r is 1 and s is n, or r is n and s is 1. So this is the formal definition of a prime number, and n is composite if and only if we have an existential statement for the definition of a composite integer. We say there should exist some positive integer r and some positive integer s, such that n is equal to r times s, and r and s are both between 1 and n. Now let's focus on how to prove a statement. In this case, we are going to see how to prove an existential statement. So if you remember from section 3.1, a statement in this form, which is there exists some x belongs to D such that q of x is true if and only if q of x, which is the predicate of the statement, is true for at least one x in set D. So we have two ways to prove such existential statement. The first way is to prove that there is some x in D, or we can find one x in D that makes q of x true. So we have to give an example of such member of D that makes q of x true. Another way is to give a set of directions for finding such an x. So we may not be able to, or we are not interested in finding the exact value for x, but we give some directions for finding such an x. Both of these methods are called constructive proofs of existence. Now let's look at an example of the book in this regard. Example 413, which says prove the following. In the first part says prove the following. There exists an even integer n that can be written in two ways as a sum of two prime numbers. So we want to see if there exists such a thing, and if there is, what's the proof? So we are going to use the constructive proof of existence. We are going to show that n equals 10 has such property. So 10 can be written as both 5 plus 5 and 3 plus 7. So if you look at these two equations, it basically writes 10 as the summation of two prime numbers in two ways. 5 and 5 are both prime numbers, 3 and 7 are both prime numbers, 5 plus 5 is 10, and 3 plus 7 is 10. So basically prove that there is some even integer n, but 10 is integer. 10 is an even integer that can be written in two ways as a sum of two prime numbers. So we are done with the proof of part A. In the second part, in part B, the question is, suppose that R and S are integers, prove the following existential statement. There is an integer k such that 22R plus 18S is equal to 2k. So in this case, if we assume k is equal to 11R plus 9S, then using distributive law of algebra, we can say 2k, which is 2 times 11R plus 9S, is equal to 22R plus 18S. So we basically use the distributive law of algebra to show that k is equal to 11R plus 9S. So we don't need to give an exact number or exact integer for the value of k. We just need to say k is equal to 11R plus 9S. So if R is 1 and S is 1, so it would be 11 times 1 plus 9 times 1, which is 20. So k is 20 if R and S are both 1. But we don't need to show such a thing. We just need to say k is equal to 11R plus 9S. So it is true for any R and S that someone picks, and it just proves the existential statement using constructive proof of existence. In the next subject, we talk about how to disprove by counterexample. So usually when we say disprove by counterexample, we want to disprove a universal statement or a universal conditional statement. In this case, as you see, we have for every real numbers a and b, if a squared is equal to b squared, then a equals b. We want to disprove this universal conditional statement by counterexample. Let's see how we do that. To disprove this statement, we need to find two real numbers for a and b such that the hypothesis of the conditional statement, which is a squared equals b squared, is true, but the conclusion is false. So the conclusion is a is equal to b. So a is equal to b should be false, but a squared plus a squared equals b squared should be true. In this case, we assume a is equal to 1 and b is equal to negative 1. So in this case, a squared is 1 squared, which is 1, and b squared is negative 1 squared, which is again 1. So a squared is equal to b squared, so the hypothesis of the conditional statement is true, but a and b are not equal because 1 is not equal to -1. The next method for proof which we talk about here is method of exhaustion. In this method, we need to try all the possible cases and to make sure that all of them are true in order to prove a universal statement. So consider this example. For every n belongs to z, so for every integer n, if n is even and n is greater than or equal 4 and less than or equal 26, then n can be written as a sum of two prime numbers. In this case, we have many even integers that are greater than or equal 4 and less than or equal 26. We need to try all of them to see if they all satisfy this condition, which is they should be written as a sum of two prime numbers. So the solution would be 4 is equal to 2 plus 2, so that's correct for 4. For 6 can be written as the summation of 3 and 3, which both are prime numbers, so that's true too. How about 6? How about 8? 8 can be written as 3 plus 5, that's true. How about 10? 10 is equal to 5 plus 5, true. 12 is equal to 5 plus 7, true. 14 is equal to 11 plus 3, that's also true. 16 is 5 plus 11, 18 is 7 plus 11, 20 is 7 plus 13, 22 is 5 plus 17, 24 is 5 plus 19, and 26 is 7 plus 19. So we use the method of exhaustion to prove that a universal conditional statement is true. So it took us a long time, but we checked all the different cases that may exist for the value of n. So n should be even, and n should be greater than or equal 4, and n should be less than or equal 26, and we checked all the cases. But this method may not be true all the time, because sometimes we have infinite number of cases for, or infinite number of values for a variable like n, so it would not be practical to use exhaustion to prove such a universal conditional statement. Another method that we address in this chapter, which is very important method, is the method of direct proof. The first step of such method is to express the statement in a formal way. So usually we express the statement to be proved in the form of a universal conditional statement. For example, for every x belongs to D, if P of x is true, then Q of x. This step is often done mentally, but I strongly suggest you to write down this step. The second step is to start the proof by supposing x is a particular but arbitrarily chosen element of D for which the hypothesis P of x is true. So basically, we are going to assume that x is an arbitrarily chosen member of D, which satisfies the hypothesis, which is P of x. And then in the last step, which is the most important step, we need to reach to the conclusion. We need to show that Q of x is true by using definitions and previously established results and the rules for logical inference. So this method of direct proof needs a lot of practice. You need to solve many examples using this method and prove different statements using this method to sort of master such method. Let's look at the theorem 4.1.1 of the book, which says sum of any two even integers is even. Let's prove this using the method of direct proof. In the first step of direct proof method, we need to formalize the theorem. It says the sum of any two even integers is even. So the formal way would be for every m and n as two integers belongs to z if m and n are both even, then m plus n, which is the summation of these two integers, would be also even. So what is the assumption here? M and n are even integers. What is the conclusion? M plus n is an even integer. So how about the second case, the second step of the proof? In the second step of direct proof method, we need to sort of come up with this argument that m and n are particular but arbitrarily chosen even integers, right? So what is the outcome that we need to reach? What is the conclusion? We must show that m plus n is even, right? So how to reach from the assumption or hypothesis to the conclusion? In order to reach from hypothesis to conclusion, we need to use the definition of even numbers. So since m is even, m can be written in the form of 2 times r, where r is an integer, and also n can be written as 2 times s, where r and s are two integers. So m plus n would be equal to, by substituting m and n with their respective values, m plus n would be equal to 2r plus 2s. And then by factoring out the 2, we will reach 2 times r plus s. So r plus s is the summation of two integers, and since integers are closed under summation, so r plus s equals to t is a new integer, okay? And as a result, m plus n can be written as 2 times an integer. In this case, that integer is r plus s. So by the definition of even numbers, m and n also becomes even. That's how we proved the theorem 4.1.1.